So I think we can say good evening, almost everyone. And yeah, it will take an hour, so get ready. This presentation is mostly code. It's not, there are slides, and of course I will share slides because I need slides to control my flow and to control if I tell you everything I planned to tell you. So there are slides, but I will spend the majority of time during this presentation in IDE, in console, because I think it's the most interesting thing, and the truth is in the code, not in the slides. Slides accept everything. Everything works on slides always. So a few things about me. So I'm Jarek. I live in Kraków, Poland. At the moment, I work as a performance benchmarking engineer at Neo4j, a company which builds native graph database in JVM, which is a totally crazy idea. Still, I think building databases is a crazy idea, but building database in JVM is even more crazy. So I'm professionally with JVM for over the last 20 years, with some breaks, like, I was doing stuff in EC, in Python. Then I had a quick adventure, not so quick, almost 3 years as a manager. I wanted to understand why some things work this way. They work in business, so I decided to switch for a moment. But now, for the last, I think 10 years, I'm back to business, and the older I get, the closer to bare metal I get, and the more I'm interested in low-level performance stuff. So that's me. Yeah, I speak at conferences a lot, sometimes too much, and I'm founder of one of the conferences in Poland, the SecPod conference, and also we have a Facebook group, but it's mostly in Polish. So connected with the topics we discuss on this conference. So that's about me in short. Okay, probably you don't know me because yeah, I don't travel a lot outside of Poland for conferences. Yeah, so there's one thing really important sometimes. Yeah, my presentations can contain strong language, my opinions, and I will talk about things people feel not so well about, but yeah, that's me. You have to deal with it, unfortunately. So, but what I realized, it doesn't happen often on online. It's like on offline conferences, I was more to raise some topics. Okay, so the title of this presentation is if everything is under control, you are not going fast enough. And this is a quote from, I think, a Formula 1 driver. I don't remember exactly the name, but I think it's a nice description of what will happen during this presentation, because this presentation will be about performance, some specific take on performance. So we will be not looking at end-to-end performance system. So this will be not about performance of your Spring application or performance of J2E container, whoever is still using it, but it will be about performance of your code. So something that is usually called in the performance testing world micro benchmarks. So we will be we'll get to know tools, techniques, and some jokes about how to make your code faster at micro level. So at specific function, object, or whatever your unit is. It's like unit testing for performance. So it's micro benchmarks. The funny thing about performance, when I started doing it like a couple of years ago professionally, it was, everybody was saying to me, okay, performance is hard. Don't do it. Don't go this way. And I think it's a part true, because there are, I think, two reasons why it's hard. One reason, because you have to really know a lot from different domains, because it's not enough to know programming language or framework. If you want to be a performance engineer, you need to understand hardware. That's one thing. You need to understand your framework. You need to really understand, if you do it for JVM, you need to understand the design architecture of JVM. So you need to understand networking, and there's lots of things that you need to learn. And of course, the problem is I haven't seen a really good book on performance as a practice. So there are books about specific topics, but how to work as a performance engineer, I haven't seen a lot of books. You have these things like clean architecture that tell you, or clean code that tell you how to be a good programmer, but I think we don't have something like a clean code for performance that tells you how to be a good performance engineer. So there's a lot of learning by doing. That's, I think, the problem. For me, after all these years, I think it's fun. I really like it, and I really enjoy it. I think that's the best job I had in my 20 over years in IT. Okay, so this thing you will see, and now I'm just looking at the time, is I'll try to simulate one day from the life of performance engineer, showing you all the tools and things. So basically, how it looks like, it's I think I can use and compare it to the TDD life cycle, which we probably all know. So write test, write code, run test, refactor, and so on and so on. And in performance testing and in benchmarking, micro benchmarking, I think it's really visible. But you have the same cycle. So you write code, you write performance test, you profile your code. That's important. It's I think people think that performance is about numbers. Yes, it's interesting to see numbers, but I think performance and benchmarking is more about understanding why your system is slow, or how we can make system faster. And the numbers don't help you. The numbers are end game. It's like fine to show it to non-technical people, but if I say that something runs 100 requests per second, do you think it's slow or fast? It doesn't give you numbers. It doesn't give you anything, except this is a way to track your improvements in the code, but this is not something that can tell you what's wrong. So that's why the profile is important when you analyze the recordings, and when you make improvement and repeat the cycle over and over again until you are satisfied, or your boss is satisfied with the performance of customer, whoever. And I think performance as a practice, like testing, coding, whatever you do in IT, it's like everything in life, requires passion, practice, and persistence. It takes time to really enjoy it. And yeah, and of course you need a good framework. So I will show you, I hope, something that looks like a good framework for performance management testing. I'm sorry, performance management is a different thing. So what we will be doing today is basically we will take a really basic example, something that probably every one of you knows, and we'll try to implement it in Java and make it faster. So we will have some basic, really naive implementation. We will write performance tests, benchmarks, we will run them, run profilers, try to do some analysis and understand where can things go a little bit faster, and think about ways of making these things faster, and then we'll improve the code, run it again, and we'll have a couple of rounds until we reach the ultimate goal. So extremely fast. example. So I choose something that's familiar, I think, for everyone, I hope, and something that doesn't take like months to implement, so you can squeeze it on a couple of screens and a couple of classes. So I chose a MapReduce framework. So what we are going to do is basically, I will show implementation. I will be coding live. I will show implementation of MapReduce framework. It won't be Hadoop. This is something that will be running on a single machine, not distributed, but just for the sake of simplicity. And we will take one specific example of application of MapReduce is a distinct word count. So basically, you have a document, and you want to count distinct number of words, and how many times the word occurs in a document. And it will be quite large document, so we cannot do the simplest possible way. So yeah, let's go to the code. There is a mistake in the slide because just the day before the presentation, I decided, okay, let's go with Java 17, which was released a couple days ago. So examples are compiled and run on Java 17, latest and greatest Java. I have some surprise. I have comparison of of runs between JDK 11 and 15, and if time allows, I will show you the speed difference between JDK 11 and JDK 17. I will use Java Micro Benchmark Harness, JMH, the async profiler, Java Mission Control, and flamegraphs. All the tools are open source and free to use, so you don't have to worry. So let's talk about a little bit quick introduction how MapReduce works. So basically, how this algorithm works, it divides your input, whatever it is. It can be a text file, it can be rows from database, it can be a set of JSON files, whatever. It's really abstract. It divides it in smaller chunks and runs map operation, which emits a value. So every entry, every value you give to the framework, first is passed to the mapping function, and this mapping function emits sets of key values. I will show in the code how it looks like. And then when you have this huge list of key values, then you run reduce operation to get the final result. When I show you the word count example, I think it'll be easier. So we have a couple of basic interfaces. One is input, which basically fits the algorithm. So I use the iterator, and you call next, that gives you the next entry, next data to the algorithm. Then you have a mapper, so something some kind of input. It can be whatever. In our case, it will be a line of text, because we will take this file and split it into lines, and every line will be passed into the mapping function. And then we have output. So output is where we emit, where we write this key value pairs. Okay. Offline events. I don't see your feedback if it's okay, but I assume it's okay. Then we have a reduce function, and reduce function, it takes a key. So for every key, we call reduce function, and we pass this key and a list iterable all the values emitted by mapper function to this key. And of course, we produce some output from the mapping function and from the reducer. And output is really simple. We just emit a pair of values, key and value. Okay. What is the most, like, the MapReduce is a famous white paper, and it was published by Google, and it's a really large and huge thing, and probably many of you heard about Hadoop Spark and all the frameworks implementing MapReduce, but this is MapReduce on the simplest possible version of MapReduce I can come up with. So basically, we go through the input, we call map on the mapper on everything what we get from input, and once we have it, we call reduce for all keys with the values emitted by the mapping functions. That's MapReduce on the smallest possible slide I can come up with. So of course it's a framework, so we need an implementation, and the implementation is word count. So I call it hello world of MapReduce. So what we want to do is basically we take a line from a text file. We want to split this line into words, and for every word, we will emit this word with number 1. Okay, with 1. So at the end, we'll have a huge collection of this key value pairs when the key is word and the value is 1. Of course, to make this algorithm a little bit fancier and something to optimize for, first, we will use this kind of regex to split the line into words, and we will filter out stop words. So, all the short words like and, or, by, the, then, and so on, but there's a lot of these words, and they probably for our analysis are not required. We will filter out these words. So basically, this object stop words contains all the words, stop words specific to a language. Every language has a lot of has a list of stop words, and so we will filter out, and this is just for sake of the demonstration. And then we have, as you can now imagine, what the reduce function will do. It will simply make a sum, count the number of occurrences of this word. This way, we'll have a distinct word count implemented in MapReduce. Trivial, I would say, but I hope you're with me. So let's imagine that we created this code. I can now, I think, yeah, I can show you the full implementation. So as you can see here, we have where's this fancy thingy? Yeah, so basically this is our implementation. Okay, exactly as I showed you on slides. And you did it, and somebody said, okay, is it fast? What would you do? You have a couple of options, and I think the thing I'm going to show you, Java micro benchmark harness, is like kind of standard in the Java micro benchmarking world. Everybody is using it. So you write a benchmark, and if it looks similar to JUnit, that's fine, because basically you have a method that you are going to benchmark. So this is our benchmarking. This is what we are going to benchmark, and this is our example text that we are going to use during the benchmark. And then we have some tear down and setup and some parameters that comes to your benchmark. And you run it, you compile it and run it. I can show you what it looks like. So basically, I can do something else. Once you build it, you will see that it will create, this framework will create a jar, and if you run this jar with -l, it will show you all the benchmarks it found in this jar. So basically, because it's cool. Because it uses regexpress, you don't have to put like full name of the benchmark. It's enough to put, you know, the part of the benchmark name. So what happens now is it tries this benchmark, this framework tries to run as many times as it's possible your benchmark, so your method. What it does, it first does the warm-up phase. So basically tries to warm up JVM because we know it, JIT, GC, caches, and all this nice things needs to be warm up. And after the warm-up phase, you will see the measurement phase, and measurement phase will tell you how fast it is. So as you can see, we started with this number of operations per second. So we were able to execute 0.6 benchmark per second. And now I think it stabilizes, and then it will go to the measurement phase, okay? But still, we don't have an answer to question, is it fast enough? Is it like the fastest possible implementation? Could we make it better? And this is where we get some help with from something called async profiler. So async profiler is a profiler created, I think, 4 or 5 years ago, which uses a special call in the JVM called get async stack trace, which is more precise and more valid than other profilers. I think commercial profilers started to use this method some time ago, but since I switched to async profiler, I don't know what happened in commercial. So one interesting thing is async profiler shows you this. This is a flame graph. So basically, this is, you know, the 100% of time, running time. And then what you see here is, you know, how much time the benchmark spent in specific methods. And as you can see, here is our run method in our framework. So this is where we start doing the word count. And then, as we can see, the majority of time we spent in a mapping function. So this is our word count and our mapping function. And if you go deep, we see that we've spent like 125, I mean, one fourth of the time in regexp expected in something. We can expand it later. And then we spent a lot of time in this class, stopwords, okay? So, you know, from the performance engineer is like, okay, the good candidate, you always start from the big ones. You don't bother things that are tiny and don't, at some point in the beginning, you just want to gain as much as possible with like single change. So you go to this class. Sorry. So this is the class that is doing the filtering of stopwords. And we don't do a simple contains and comparing strings using compare, but we use collator. Collator is a Java class that knows how to sort and compare strings based on the language. So, you know, you shouldn't compare word in English and shouldn't compare certain word in German because the sorting order is different per language, and comparison is also different per language. So we use collator, and as you can see, what we do every time we call contains, okay, we get instance of the collator. So we spend a lot of time, you know, constructing this collator. This is this thing, get collation key. And it takes time because we do it on every single line. We call and create new collator. So if you are familiar with Java, you would say, okay, so maybe what we will do, we will create a single instance of collator and don't call it constructed every time. Of course, collator is not thread safe, so we can do a nice hack to this, okay, and create collator as a thread local. And this is the implementation, but as you can see, I can make it this, and I can. So here we have a version where we create the instance of collator on every call, and then we have version that we keep the instance of collator in the thread local. Okay, so this is one improvement. Once we run it, you will see that the flame graphs got different, and I will show you in a moment that numbers got different. So with the not thread local stopwords, this is our performance. With thread local, we get a little bit better, but not perfect. So if we could keep trying, we'll find that there is implementation of collator provided by IBM. It's called ICU, the name of this library. And you can use ICU as a replacement for the standard Java collator. And we replaced the standard Java collator with the ICU, and we got it like 2 times faster. Okay? So this is basically the way you work with code. And of course, every time you run it, and every time you look at the flame graphs and see how they change. I will skip a couple of slides because I think it's less interesting. But there is, or maybe I will show you. As you can see, this is optimized version when we use ICU thread local and we use different collator. And you know, the flame graphs are different because now we see that we spend a lot of more time in pattern split. So we could like optimize and not use regex. Maybe string tokenizer will be faster or something else. But there's another thing. We have this output. Yeah, you have this class output. You can go and I can close it. First. And we, of course, need some implementation. And the easiest implementation I can think of is to use hashmap. Yeah, because if we emit key value pairs, the obvious choice is to write this thing to hashmap. And of course, because one key can have multiple values because you can emit the same thing with different value many times. So we need to simulate multi-value hashmap with standard Java hashmap. And the best way to do it is to just use compute and create a hashmap which keeps a list of values. Okay, so this is our basic implementation. And as you can see on flame graphs here, it takes some time, especially the method compute is quite time consuming. So maybe we can find a better solution, a better way to storing multi-value keys in hash maps. And of course we can, because we can use Guava and we can use multi-value hash map from Guava, or we can use Eclipse collections and we can use the multi-value hash map implementation from Eclipse. Okay, so just to show you how it looks like, we have now then, I'm still mixing shortcuts. It's Guava. So it's exactly the same thing, but we use array list multi-map as an implementation. And then we have Eclipse, and we use mutable multi-map. So we have different implementations of the interface. And how do they compare? I again can run it. And as you can see, the fastest thing is the Guava. In this case, I'm not saying that Guava is always faster, but in this specific case, Guava is faster, hashmap is second, and Eclipse is the slowest one in this specific case. I was investigating why Eclipse is slower, and it looks like it produces a lot of garbage. So there is, the garbage collection taking time. So yeah, it looks like Guava is better optimized. for our case. And I think this is a quote what I really like, and I think it's super important. It's like people try to get to the optimization too early. Like even if they don't know if they need it, they try to optimize it, or sometimes they totally completely ignore the code optimization and making code faster. And I really like this quote for Wes Dyer. I think he worked in Microsoft, and in this article he wrote that, you know, first make the code correct, so you know, make sure that it does what business is expecting it to do. Then make this code clear, so you can understand and everybody can read, and your teammates, you know, don't get lost in it. And then make it fast. So because what you will see in a moment, optimized code is harder to read. It gets, you know, like a dark corners. The optimized performant code will not be easy to understand. And if you start from like messy code and you try to make it faster, which will make it even messier. So yeah, I think making code clean is like the most important part before you start to implement. Make it optimize. So can we do better? Like we see two optimizations, like one is to like avoid allocation and store things in the thread local, and the second optimization was to find just simple faster library. Two ways of making code faster, but can we go faster? One thing that you will notice, this implementation is really naive. It's single-threaded. So of course, if you want to go faster, there's only one choice: more threads. If you have questions, just write them down. I am trying to answer. I know I go fast, but we have a lot of material to cover. Threads, and this is like my lesson learned. Never ever start with concurrent implementation. Make your single-threaded implementation as fast as possible, and then try to optimize it, because it's really hard to then prove that it's doing what it's supposed to do and it's correct from the business features and the requirements perspective. So quite often what I do, I have a single-threaded implementation. I have JUnit test for it, and then when I write multi-threaded implementation, I make sure that they pass the same test suite. So I have some baseline to compare. What we can do, and this is where MapReduce shines, because we can use the classical divide and conquer. We have text file in our case. So what we can do is we can take and read line from this file and send every line to a separate thread to call the mapping function. Okay, so we'll have how many threads we want, and we will run it in parallel, because it's really interesting, a nice algorithm to parallelize. And then once we run through all till the end of the file, then we will have our reduce phase. And the reduce phase, if we will have like 2 hours of time, we can also do concurrent. But because we have 1 hour, we will just focus on making the mapping phase concurrent. Because also, if you look at this, here is our reduce on the left of the screen, and it doesn't take much time because our reduce is simple summing, adding some numbers. And here, the mapping is problem. The mapping takes time, so we will gain more by making a mapping function parallel. So how we can do it? This is not presentation about Java util concurrent, but in the Java util concurrent there is funny thing called phaser. So basically, how phaser works, you register your job, your work in a phaser. So this is this line. and then you send this job to some executor. And once the job is done, basically here, it will say, I'm done. So I can show you, it's like use. So here we'll see it. So we take a line from a file, we register a new job in Phaser, we send this job to the executor service, to thread pool, and then in job, here is our job. At the end of the job, once we are done with all the stuff we're doing, we say, okay, I'm done. I did my job. So this way, the Phaser knows when you stopped processing something. So as you can see somewhere down here, we do on the Phaser, we say, wait until all the lines of file text are processed, and then move to the reduce phase of this algorithm. I hope it's clear. So yeah, what can go wrong? Nothing, everything will be fine. So of course we write the test for the parallel implementation, and as you can see, it got faster. You know, we went from 2 operations per second to almost 3.5. These numbers were taken for, I think, JDK 15, so they will be different with JDK 17. And this is an 8-core machine. So as you can see, we are not fully utilizing 8 cores. We didn't went like 8 times faster. We had some nice improvement, a little bit faster, but not so much faster. So what we can say, okay, so let's start and see if we add more threads, it should be faster. And as you can see, it won't. And here we have, this totally different presentation, the universal law of scalability, and Amdahl law. So as you can see, as you add more threads, the things get slower. Different presentation and different topic. So adding more threads doesn't help us at all. It makes things worse. There's another tool we are using. It's Flight Recorder. I think it's free from Java 11. Before this, you had to license on Java because this tool is part of JVM. But since JDK 11 is free, or JDK 10, so I won't tell you exactly how it works because time. But what it gives you, it shows you different insights of the virtual machine, of different things. And one interesting thing when you run JMH, your benchmark with this profiler, is it will show you how much time you spend in logs. Okay, so as you can see, we are spending quite significant amount of time waiting on different logs from different threads. And if you go back to here, you don't see any logs. Yeah, it's like, hey, no synchronize, no reentrant log. Where do we have these logs? I know we have logs hidden in 2 places. One is concurrent hash map, because we cannot use now the regular hash map because we have multiple threads. We'll try to write to this map. So it won't work with HashMap, it won't work with Guava, and it won't work with Eclipse collections. So we had to use like concurrent HashMap. This implementation uses global, per whole system concurrent HashMap. And you have, as you can imagine, you can have millions of threads trying to modify and put things into this HashMap at the same time. So this is the source of latency in this example. where we are basically, as you can see here in the top, but we are spending a lot of time on concurrent hash map and locking in concurrent hash map, because this whole thing is quite busy. There is another issue with logging, but it's like hidden by the problem. What's interesting in performance is sometimes you fix one performance problem but uncovers the other performance problem. But you know, this another problem was so tiny it was not visible, because you know that the calculations time was dominated by this specific problem. Once you remove it, you will see on the surface another performance problem. And this another performance problem is here. Okay, as you know, in executor service, what we have is a queue, and on the queue we keep tasks, and at the end of the queue we have a set of threads that pick up things from the queue and execute these tasks. And as you can imagine, if we have a lot of tiny small jobs, and in this case we have really, you know, lots of tiny small jobs, because we have single lines of text and every single line is a single job. So we have threads competing for access to this internal queue in the executor service to get new tasks. Okay, how we can solve this? Actually, we can do two things. One thing is get rid of the global hash map, okay, and make sure that we will have a thread. Every thread in the thread pool will have its own hash map. And what we will do is we will do the mapping phase, and every thread will have its own hash map. And at the end of the mapping phase, we'll take all the partial hash maps, merge them into one big, and then do reduce. Okay, of course it's a hypothesis, and this is also the part of work as a performance engineer. It's like you make a hypothesis that something will be faster, but you never ever trust your gut feelings. It's your worst enemy in this case. You just say, okay, I will make an implementation, but we'll have a hash map per thread. And maybe, this merging will be so fast, but in total, this algorithm will be faster. Maybe merging will be slower, and we will have fast access to hash maps because they will be per thread, but the merging will be slower. We don't know. So it's worth to check. The second thing what we can do, and it's quite popular optimization technique, it's batching. In place of putting a single line to this function, we will batch lines in 100 or 200 or 1000 and send these 1000 lines into the queue for mapping. This way will reduce contention because we'll have longer tasks in the queue. We'll also produce slower because it will take time to create another batch of work. So we'll reduce contention. This way, things should get faster. And into our batching implementation. How we are of time? Quite good. Where it is? Yes, it's here. So what we do, we create a batch, and then we first add things to the batch. So we add our lines of text into the batch. Once we reach the size of the batch, or we reach the end of input, we register new task, but this task this time is a set of files, set of lines, set of inputs. Yeah. And in the mapping phase, oh, this is nasty code, man. As you can see, we started with something really Yeah, this is what we started with. Okay, after two passes of optimizations, we are with this monster, and especially this monster. So this is just the proof that if you want to optimize the code, it will get messy. So we have our phase, as you can see, where we run multiple files because this is our input, our batch. And then we send the partial results somewhere to the queue, and we say we're done with work. Now I look at it, and we could do better, actually. I have a feeling that it can be even faster implementation. Sorry. So what we have at the end is a set of maps from thread pool. So we add an extra phase, and somebody would say, okay, you add an extra function, it will be slower. Not necessarily, because if the increment from the speed up that we don't compete for resources, like for the queue and for what's the name, for the queue and the concurrent hash map, if we don't compete it, the increment from speed up will be bigger than adding one more step which will merge results. So here is our merging functions, which function which gets a list of hash maps, collection of hash maps, and we do nice merge. And while I was implementing it, I would say, okay, we are merging hash map. Can we actually merge and reduce at the same time? And this is oh yeah, we can merge hash maps and reduce them at the same time. So we don't have, as you can see, yes, this implementation, yeah. So here we have a reducing operation. Sorry. So we merge the hash maps and reduce them at the same in the single pass of the, of course, parallel stream to make it faster, because it's big enough set of data to benefit from parallel stream. In this case, trust me a little bit. So is it faster? Let's see. So the problem we had contention on the blocking queue in thread pool, and we had contention on concurrent hash map. We removed contention by adding batching and by removing the global concurrent hash map and having hash maps per thread. So we use also batching for this. And let's see the numbers. As you can see, even with adding this extra step for merging, we are now really faster than the original implementation, single threaded implementation. We are getting too close to something. It's actually on Java 17, it's actually 3 times or 4 times faster, the batching, mainly due to the changes in garbage collection implementations in Java 17. Can we go faster? This is the mantra. If you work as a performance engineer, can it be faster? Can it be faster? This is the part of code I'm really not proud of, but I trust you guys. You won't tell anyone you saw it. So there is ForkJoinPool, and I don't know how much you know about ForkJoinPool, but basically, in a nutshell, what it is a work stealing pool where you have a queue per thread. So you don't have now one big queue for all the tasks and then many threads working on the one queue. You have many queues. Sometimes I think it's called multi-lane. you have many queues, you put things on these queues by random, or whatever algorithm you say you use to produce things and put, and then every thread consumes things from its own assigned a queue for him. What is even more interesting, and that's why it's called work stealing, when the worker, the thread from the thread pool, comes to the queue and sees that it's empty, it tries to steal work from the neighbor. So it goes to another thread pool's queues and tries to steal the work. So it tries really hard to like max out your CPU. So you don't have threads that are waiting, not doing anything. And this is like the, it's ugly. It's really ugly implementation of the ForkJoinPool. Don't tell it to anyone. I'm not proud of it, but it proves my point. Because if you run this dirty implementation of ForkJoinPool, you will see that it's got even faster. Even my dirty implementation, without all the proper things that I should use in ForkJoinPool, like manage blocker and count to completer, that's a different presentation. It's like really the most basic and abusive implementation of ForkJoin. It's faster. So this is the fastest implementation of our algorithm. So to summarize this journey a little bit, because we are getting closer to an end. I'm just switching windows. We started from this. It was in only 70 lines of code and really simple, naive implementation. Then we did this, and parallel many threads, and it's like 120 lines of code. Then we went to batching, which got crazy because it's 170 lines of code, but we don't have shared structures almost. I think I can make it even better. And we ended up with dirty implementation using the same algorithm, using ForkJoinPool and ForkJoin framework. And it got shorter. Yeah. In this case, with ForkJoin, it got a little bit shorter because it's like really dirty implementation. And with each such improvement, what we did, I really want you to remember, it's like you make a hypothesis, like however crazy it sounds, like with this red, adding the merge phase, just check it, because your brain and your knowledge and your gut feelings will trick you all the time. And I think assumptions are the worst enemies, the biggest enemy of somebody trying to optimize the code. Assumptions that you had in your head, or assumptions you saw on Stack Overflow, or assumptions you read in the book. Just, use JMage or whatever to prove your assumptions, or prove them wrong, or confirm that everything works. Are we done here? The original presentation is like 2 hours, but I did it only once because somebody asked me, and it was offline, so much easier. We could do break, because yeah, as you can see, it's like a drug. You make a modification, you see that it's faster, and you say, okay, maybe I can implement it and make it even faster. So don't get addicted to it. What's interesting during the, this is, I think, mistake, because it's a 6 GB file. So we use a quite, like, these days 6 GB doesn't impress somebody. But the problem is that when I try this in my implementation using 100 GB file, all the implementation, single-threaded, multi-threaded, ForkJoin, and so on, end up with out of memory. Because if you followed me, we keep a lot of partial results in memory. So we have hash maps with, the values and keys. And what explodes with huge file, the bigger the file, the bigger the hash maps we will have. So this algorithm is not ready for huge files. So what we can do, there are like couple of options. One, we can like flash things to disk, and somebody will say, hey, it will be slower because it's disk. No, if you flash async, if you have a separate thread that flashes things to disk, because from your perspective, you don't care. You just want to get reclaim your memory and then read it later from disk. But for now, the only thing that is interesting to you is like flashed as fast as you can. So you can use some async things. Of course, you will pay serialization and deserialization costs. And here is the whole discussion. Maybe it will be, for sure, it will be slower, the disk. But then there is a lot of nice optimizations you can do, like changing the serialization format and serialization for maybe libraries and so on and so on. And one interesting thing is, because the way this algorithm works, you don't have to wait until you do all the mapping. Yeah, you can start doing reduce as you get things from the mapping function. So maybe it will be good to sacrifice some threads and say, okay, 6 threads on 8 core machine will do mapping, and 2 at the same time will do the reduction. Because when we do reduction, we don't need to keep the the intermediate map in memory. Probably there are more things we could do. So one thing I want to make sure that we will get from this presentation is measure, don't guess. I will send all the details. The code is open source, and everybody can play, download it, and comment and find better ways and faster implementations for these things. This is what I was able to do in like 4 days when I was preparing this presentation. Of course, if you are interested, I'm doing courses on JVM performance. So if you want to, you're welcomed. Yeah, I think. Yeah, almost hour. I'm done.